Okay, so this is chapter 21 or chapter 22. I don't remember the exact number, but I think it's chapter 22. Yes. So chapter 22, and it's current, electricity. So in the previous chapter we talked about static electricity, meaning the electric charges that do not flow. But here current electricity means the charges that flow through the material. So usually in conductors you have free electrons, and those free electrons are free to move in the conductor. Okay, they are not bound to the nucleus. And if you apply some external force in form of electric field, then those charges will be pushed by the electric field. As a consequence, they flow through the conductor. So you have a conductor, okay, and this conductor has lots of free electrons, and if you push these electrons, how do you push the electrons? You basically apply electric field, okay, and these electric fields exerts force on the electrons. So these electrons will move in the direction opposite to the electric field. So that would be the, so these electrons will flow in the direction opposite to the electric field with some velocity. Okay, and the flow of electrons is what we called current. So current is nothing but it's the flow of electrons. Through a conductor. Okay. Now at the time when Benjamin Franklin discovered the charges, positive and negative, he didn't know what negative charges are. He didn't know negative charges are electrons, and he didn't know positive charges are nucleus or protons. Okay, so people then, those days, they thought that the charge that flows in a conductor is positive charges, okay, not electrons, because again people didn't know what protons and electrons are. They only knew there were two types of charges, positive and negative, and they thought the charges that flow in a conductor is positive charge. Okay, so these positive charges flow. But now we know it's the electrons that flow in a conductor. But we still use this convention where we assume that there is flow of positive charge in a conductor. This convention is what we called conventional current. Conventional current. Okay. Again, it's the flow of positive charge through a conductor, which is not the actual flow, but we still use it because people don't want to change it. Okay, we have been using this for a long time. So from now on, whenever we talk about flow of charge, we would be talking about flow of positive charge, which is just opposite to what happens in a conductor. In conductor, the flow is actually the flow of electrons, but we still consider this. It won't make any difference in our calculation or our different kinds of theories. Okay, so how do we define current mathematically? So mathematically we can define current as, current is rate of change of or rate of flow of charge through a conductor. So, rate of flow of charge through a conductor. So, the first one I wrote here, it's the layman definition, but more formally or mathematically, current is rate of flow of charge through a conductor. Okay. So, whenever you see the word rate, it's the ratio. Okay, it deals with the ratio, and in this case, in physics mostly when we talk about rate, we talk about the ratio of something over time. Okay, so in physics, rate means ratio of something over time. Okay, something over time. So in this case, current is the ratio of charge, because it's the flow of charge. So charge over time, and current is denoted by letter I. We don't want to use C here because we already used C for capacitance, so we don't want to use C. Instead we use I. I is current. Charge is Q. Sometimes I write capital Q, sometimes small q, both are fine. Okay, both represent charge, and time is denoted by T, small letter t, not capital. Okay, capital letter T is reserved for something else. It's a small t for time. Coulomb is the unit for charge, so that's measured in coulombs, C, and time is measured in unit of seconds, which is S. So the unit of current is coulomb per second, and it's also called amperes. You guys might have heard about amps. So amperes. In short form, it's capital A. Oops. So let's see an example. Consider a conductor and a charge of, let's say, 5 nanocoulomb flows through this conductor, flows through some surface area from some surface. So let's consider this surface and assume that there is a meter at that surface. Okay, so we have some kind of meter placed at that surface, and we are measuring how many charges flow through that surface, and we see that every 5 minutes, we are counting every 5 minutes, every 5 minutes 5 nanocoulomb flows through that gate or to that surface. Okay. So then what is the current in the wire? So from definition of current, current is I is Q over time, and charge is 5 nanocoulomb, 5 times 10 to negative 9 coulomb. Time is, we are measuring at every 5 minutes, change that to second because time is measured in seconds. 5 minutes is 5 times 60 seconds, and then if you do the calculation, five and 5 cancel, times 10 to negative 9 over 60. So that's 1.67 times 10 to negative 11 Now let's see. Yeah, okay, that's that amperes. Okay, now that's a very small amount of current. Okay. So that's the current. Now let's look at a worksheet problem. So number 1 from your worksheet problem. Okay, so let's see, here is the question. So you have some kind of cell. So this is from, no, this is homework. Is this? I don't remember if this is homework or worksheet. So this may be homework. I don't know. So here is a question. Okay, so I'll just explain the question. You have some kind of cell. Okay, and like we discussed last time, in a cell there is exchange of sodium, potassium, calcium inside and outside the cell. Okay, and in this particular case we have exchange of potassium inside and outside, and for the exchange we have what we called potassium channel. Okay, so we have these tiny channels that helps exchange of potassium inside and outside the cell. So this is K channel, and it says the diameter of this channel. So if you enlarge this, you see this kind of potassium channel. This may not be the actual representation, but just for simplicity we use this kind of thing to make it easier to visualize. So the diameter here, d, is 0.3 nanometer, and it carries, so this one carries current of 1.8 picoamperes. So current is given. So every time the potassium is exchanged through that channel, there is current of 1.8 picoamperes, which is, pico means 10 to minus 12 amperes. So it's asking how many potassium ions pass through the channel if the ion channel opens for 1 millisecond. So number of potassium ions is unknown, and we want to know the number of the potassium ions for time is equal to 1 millisecond. 1 millisecond means 1 times 10 to negative 3 second. Okay. So how do we find that? So this is basically arithmetic problem. We don't even need to use any formula here. So we have I means, just look at the unit. I is coulombs per second. Okay, and each potassium has, so one potassium has charge of 1. So there is one free electron in potassium, or one free proton, you can say whichever charge you want to call. If it is positive, then it's positive ion. So each positive ion has 1.6 times 10 to negative 19 coulombs. That's the charge of electron or proton. So in this case it's a proton, it's a positive charge, positive ion. So, by using simple arithmetic, so if we do Coulomb over Coulomb per let's see this one. So, Coulomb per second over Coulomb, we can get number of ions per second. Right. So, just do the unit arithmetic here. We can cancel Coulomb and Coulomb, then we get number per second. So, to get the number of ions per second, number of potassium ions per second, we can do this math. Let's see, I is 1.8 times 10 to minus 12 coulombs per second, which is amperes. Okay, that's the current. And then each potassium has the charge of 1.6 times 10 to minus 19 coulombs. This is the charge. That means if we do that math, we get 1.125 times 10 to 7 per second. So, that is the number of potassium ions that is flowing through the channel per second. But that is not what we want. What we want, if you read the question, it says number of potassium ions for 1 millisecond, number of potassium ions over 1 millisecond. So, this is the number per second, but we want number per millisecond. So, we need to do a little bit of arithmetic here. So, that means you multiply this by the time, 10 to 7 per second times second. So, second is, I mean, times the time. Time is how long we want, 1 times 10 to negative 3 second. So, that gives us 1.1 times 10 to 4 ions. Okay. So, that is the number of ions that flows through the channel over 1 millisecond time. Okay. So, let us look at next question from homework or worksheet. I do not remember what this is. So, the question is, so during the depolarization of cells, nerve cells, we talked about this briefly last time, the positive and negative charges are exchanged in and out. So, initially in the polarized state, the outside parts are positive and inner parts are negative. Okay. So, that is the polarized state, and during the depolarization, the charges switch from positive to negative and negative to positive. So, this becomes negative and the inner one becomes positive. Okay. So, when you have negative and positive during the depolarization, there is, so we know that whenever there is difference in charge, we have potential difference. So, let us say the potential difference between inside and outside the cell is not given. Okay, we don't have potential difference, it's not relevant probably. So what it says is, during the depolarization there is a flow of charge. Okay, there is flow of charge from inside to outside, and whenever there is flow of charge, we know there is current. Okay, current we know is defined as flow of charge, and it says that there is 36 picocoulomb of charge flows in 2 milliseconds. So there is flow of 36 picocoulomb of charge every 2 milliseconds. Then what is the average current in the cell during the depolarization? So we want to find I. It's pretty straightforward. So we know the formula for I is Q over T. Charge here is 36 picocoulombs, which is 10 to negative 12 coulombs, and the time is 2 milliseconds. 2 times 10 to negative 3 second, that gives us I. Okay, and I is measured in amperes. You can also say coulombs per second, but usually it's measured in amperes. So whenever we talk about flow of something, there is always resistance to the flow, like you saw in physics 1. When an object is moving on some surface, it feels some resistance due to the surface or due to the air. Okay, just like that, in conductors also, when the charges flow in a conductor, they feel some kind of resistance, okay, or opposition. So when these are flowing, there is resistance on resistance to the current. So why there is resistance? What causes the resistance in a conductor? Like we saw in physics 1, when you drag something, what causes resistance is friction, right? Or air drag. If you are running or driving your car, air drag causes the friction. It tries to oppose your motion. Like that, here in the wire also, or the conductor also, something causes the resistance. What causes that resistance? Can you guys guess what causes the resistance? Material, yeah, material. But what property of material causes that? So this one is conductor. Whenever we talk about flow of charge, we are not talking about the insulator. So it's the conductor. Yeah, so you are right. I mean, if we are using insulator, that causes the resistance. That's right. But here we are talking about the conductor. If it were insulator, then there won't be any flow at all because there is huge resistance. So what causes the resistance is how tightly these electrons are packed in the conductor. Okay, so when the electrons are flowing in a conductor, they bump on each other, they hit each other. Okay, and that delays the flow. That causes the dragging of the electrons. Instead of moving smoothly, okay, they hit on each other, and that causes the dragging of the electrons rather than flowing smoothly. And that's the reason the speed of electrons in a conductor is very, very slow. The electrons travel at the pace of a snail. Okay, so electrons flow very, very slowly in a conductor. It's a little bit counterintuitive because we think that electrons flow at very, very high speed, but that's not the case. Okay, they flow at very, very slow speed because of the bumping of the electrons in a conductor. They hit each other. Okay, so you have a bunch of charged particles, so they bump on each other, and that causes the, instead of moving smoothly, they just drag very slowly, drag along the wire very slowly. Now, what factors affect the resistance? There are a couple of factors that affect the resistance. One is the temperature. Okay, we know that as we increase the temperature, there is more and more vibration of the electrons, and when the electrons vibrate more, there is more bumping with each other, and more bumping means there is more resistance. Okay, there's lower speed of the electrons. So temperature, increase in temperature decreases the flow of current or increases the resistance. So increase in temperature increases the resistance. Okay, that's the one factor that affects the resistance. And the second factor is the cross section of the wire or conductor. So you compare a small wire with a small cross section versus a bigger wire with bigger cross section. Which one will have higher resistance, or in other words, in which one the electrons will bump over each other more? So you have electrons here, compact electrons. So in which one there is higher probability of collision between the electrons? Smaller one, yes. That means there is more resistance here, more resistance. So resistance is more for shorter or smaller cross section compared to the bigger cross section. So resistance depends on the 1 over area. Okay, bigger the area, less is the resistance. So they have opposite relationship. Shorter the cross section area or smaller the cross section area, more is the resistance. Inverse relationship. Second one is the length. Okay, so let's look at that. Consider a short wire and a long wire. So in which one there would be more bumping as the electrons move? Which one has higher probability of bumping with each other? The one in which electrons have to travel for longer time, or in one in which electrons have to travel for short duration? Definitely this one, right? Because electrons have to travel for longer time, so there is higher probability of frequent bumping. That means this one has higher resistance than the shorter one. So that means resistance also depends on the length. longer the length, greater is the resistance, or higher the resistance. Now, if we combine these two, we can write these two in combined form as resistance is proportional to L over A. Okay. So, again A is the cross section area, and L is the length of the conductor. Now, we can get rid of this proportional sign. Whenever we get rid of the proportional sign and turn that into equal sign, we need to use some kind of proportionality constant. In this case, the proportionality constant is what we called resistivity. Okay, so that's the proportionality constant. Rho is called resistivity of a conductor, and it depends on different materials. Okay, it's a characteristic of a material, meaning different materials have different values of resistivity. For example, gold and silver have very, very low resistivity. There is very small resistance for gold and silver, whereas for iron, the resistivity is higher compared to that of gold. Okay, and copper also has low resistivity. It's a good conductor. So, anything that is considered to be good conductor has low resistivity. So, low resistivity means it's a good conductor. Okay, the examples of good conductor are gold, silver, copper. Okay. So, this resistance is measured in unit called, it has a unit, its unit is called ohms. It's a Greek letter, this Greek letter omega. Okay. And if it is omega, then what would be the unit of sigma? Can you guys find out what's the unit of, see this rho? This is Greek letter rho, called RHO, rho. This is omega. Okay. So, it's called ohms, but it's the Greek letter omega, whereas this is called resistivity, it's the Greek letter rho. So, what's the unit of rho? So, rearrange this. If you rearrange this, what you get? So, it would be R, and this A will go on the top, and then this L will go on the bottom. So, R is ohms, A is area is meter squared, and L is length is meters. So, meter and that cancel. So, that will give us ohm meter. Okay. So, the unit of rho is ohm meter. So, you will see these kinds of questions in tests and quizzes. Sometimes these kinds of questions are very commonly asked in some standard tests like PCAT or MCAT. So, consider a wire, okay, that has resistance R. So, the question would be, if you double the cross section area, and also double the length, what will be the new resistance, or how will that change the resistance? Also, what's the new resistivity? Okay, so you double the cross section as well as double the length. So you have now 2L. Here you have L, and the area is A. Here you have 2L length, and this cross section is 2A. So let's answer the second one first. Resistivity is the intrinsic property of a material. Okay, it's an intrinsic property. No matter how small or big the object is, its value is always same. Just like density. So you have density of water is 1000 kilogram per meter cubed. That's the density of water. No matter how small, how little or big amount of water you have, this density is always same. Okay, the density doesn't depend on how much water you have. It's always same. Same thing with the resistivity. Okay, it's the intrinsic property, so it's same, no change by changing the size or shape. That's B. Now A, let's answer A. There are different ways to answer this. One way is by using the math. So we know the resistance is resistivity over resistivity times L over A. Now when we this is let's write this one, R1 initial resistance. So R2 is when we change the length and the area. So rho doesn't change no matter how much longer you make the wire or how thick the wire is. So we are changing the length. Now length is 2 times L, and the area is also doubled. Okay, so we want to compare R1 and R2. For that you can divide, let's call this second equation, divide R2 by R1, okay, on both sides. So divide R2 by R1, and then on right side also divide that rho L over A. Okay, I'll cancel that and that. You can cancel that and that, that and that, and 2 and 2 also cancel. So you get 1. So that means R2 is equal to R1. There is no change. And that makes sense because doubling the cross section you decrease the resistance, and doubling the length you increase the resistance. So there is compensation of increase and decrease. So that makes the resistance unchanged. Sometimes you may be asked, if you double the length, no, not that. So let's say you double the length, but you decrease the cross section to 1/2. Okay, so cross section is A over 2, but the length is doubled. So what would be the new resistance? So in that case, our R2 will be rho. You are doubling the length to L, but the cross section area is now A over 2. So divide that by original resistance. Original resistance is rho L over A. Rho and rho cancel. L and L cancel, A and A cancel. So this 2 will go on the top here. That's 4. So R2 is 4 times R1. So when you do this, you increase the resistance by 4 times the original resistance. Okay. So, resistance, any component in a electrical circuit that has resistance is represented by this symbol. So, this is the symbol for resistance, and this component is called resistor. Any component that has resistance is called resistor. Okay. Or you can say resistors are components in a circuit that resist flow of current. Basically, they control current flowing in a wire. You can change the amount of current flowing through a wire by introducing resistors in the circuit, because they offer the resistance. So, you can decrease the current by increasing the resistance. Okay. So, again, this is the symbol for a resistor. And in order to pass the current through a resistor, so you want to pass some current through the resistor, what you need? You need some kind of current source. Okay. So, to pass current through a resistor, you need a difference in potential. You need to maintain difference in potential, only then you can pass the current. What that means is, let us say you have a pipe that has some water. Okay. So, this pipe has water. If so, let us say you have some kind of tube here, and you have some kind of tube here. Okay. Just analogy. So, if these tubes are at the same level, same height, then they will have same pressure. Okay. That means there won't be any flow of water in this pipe. Okay. So, the water will remain as it is, there is no flow. But if somehow you raise this side or connect this side to this a tank at higher level, then you will have difference in the pressure. So, this one would be at lower pressure because it's at lower height, and this would be at higher pressure. So, whenever there is change in pressure, difference in pressure, that creates the flow of water. So, this change in pressure is needed for water to flow. In the same way, we also need to have some kind of change in pressure in a circuit for current to flow. Just like water, for water we need pressure difference of water. Here we need pressure difference of charge. So, the pressure difference of charge is what we called potential difference. Okay. What that means is we need to have more positives here and more less positives here, less positives, or you can also say more negative. Okay. So, you want to have negative on this side and positive on this side. So, this will give you potential difference. So this is at one potential, this is at another potential, so you have potential difference, and that potential difference provides the pressure that is needed for current to flow in the wire. Okay, so this is what you need. We call this delta V, which is potential difference, and the source of potential difference is a battery. So if you want to pass current in a circuit, so that's the resistor denoted by R. You want some current in your circuit. This is the basic circuit. You need a battery. Battery has positive on one side and negative on other side. That's the battery. Okay, and battery is the source of delta V, potential difference, and battery is denoted by this symbol, this long line and short line with that. Okay, so that's the symbol for battery. We'll be using this very frequently next time. So this longer one is positive and shorter one is negative, and we connect battery to some other component like resistor. Okay, so whenever you have this potential difference, now there is current flow I. So you guys see here, I'm drawing this arrow from positive to the negative. Okay, the current is flowing from positive to negative, which is not what happens actually, but again, this is just the conventional current. Okay, this is not the actual current. This is called conventional current. The actual current would be from negative to positive, because what flows in the wire is negative charge, not positive charge. But we have been using this for a long time, so people don't want to convert this, change this. So they just use this conventional current. They just show flow of this positive from this positive side of the battery to the negative side of the battery. Okay, I think that's all. We'll continue this next time. If you guys have any question, I can answer the question. Otherwise, we are done. Test is at 2 today, and right after the test, we'll have a short lab.